Our first speaker today is Bryan Dickman from Valetick Consulting Limited. He's an independent consulting. He should be talking on the origin of bugs. Bryan has over 22 years experience leading engineering teams and engineering communities in the field of design verification for ARM. In recent years, more focused on leading the effort to exploit engineering's vast data resources to drive insights and improvements to critical workflows, and he is currently working as an independent consultant.
Thanks, Mike. Right, so it's very nice, if not slightly weird, for me being here with some of my old colleagues, familiar faces in the room. Excuse the grand title, and also don't assume from this, by the way, that there's some sort of talk about evolution or natural selection. But I think Scott quickly picked up the joke on this one, I think. And you know, as we move towards the right, this was kind of like, it's not really strictly a bug, is it? But it's kind of like the biggest badass thing I think I could find. So bit of fun with the first graphic there. So yeah, I'm going to talk about where bugs come from. And you know, I think a lot of this is going to be familiar territory to a lot of people on the call. But thinking about how they actually get into design from a design perspective, and then you know what designers and verification engineers jointly together can do about that. So, Mike, I think you really covered this for me, so I can probably move on from my lovely mug shot there. So yeah, so I, as many of you know, I retired from ARM earlier this year. I was with ARM for 22 years, a big chunk of my career, and decided to move on and do some other things. And recently decided to go independent and do some independent work. So this is my company, Valetick Consulting, and I've been talking to Mike quite a bit as an old contact, an old friend. So he invited me to this slot, and also I'm talking to somebody else that some of you may know, which is a guy called Joe Convey. Is another friend of mine, also set up as an independent company. So we've got a couple of things on the go at the moment. So just some disclaimers. So what I'm showing you today is really a personal perspective on this from me. None of the data I'm sharing is real, they're sketches, right? So I'm really giving a whiteboard type of view of the world rather than presenting any real data. I don't think there's anything in here that is particularly brand new or unfamiliar. I think it's all established thinking, but I thought there was value in bringing some of that thinking together as one you know, sort of semi-coherent story. So that's the aim of the pitch. And then in order to do this, I've actually been working on a white paper, so I'm going to produce that white paper and I'll follow up with the presentation later. Keep me time, won't you? Yeah. So, question is, so why do we still have bugs and jobs as DB engineers, luckily? You know, obviously the reason for that is that finding bugs is hard, as we all know. Anybody that's been in the business for as long as we have, or certainly as long as I have, knows that this is not really a solvable problem. It never has been, and it still isn't today. And you know, I make an assertion at the start that essentially all designs will contain bugs. Even if you think your verification is clean, there will be bugs in there. When you deliver the product, it will contain bugs. It's all a question of how critical are those bugs and how impactful are those bugs, you know, if they emerge at a future point in time. So what is verification? It's really, I think of it as a quest, essentially, and it's a quest to find and expose as many of those bugs as possible. But it's also, you know, a constrained quest, usually constrained by time and materials and resources. And you know, there's really no sense of completeness here. So even if you take a structured approach to the problem and you do you know, really good detailed test planning, your test planning won't be 100% complete. If you're using a coverage methodology to try and make things measurable, your coverage model won't be complete either. And clearly, you know, we can't run infinite verification cycles, so bugs will be missed. So verification employs strategies to try and find those bugs, obviously, but I think a key thing that Mike was alluding to is that, you know, we really need to look at the design process as well and understand what can be done in terms of design to try and avoid bugs in the first place, or bug avoidance. And then I've got the, I don't know how many people have seen this, but I found this on Wikipedia. This is the Grace Hopper infamous first ever bug, which was a moth that got stuck in a relay on a Harvard Mark II computer in 1947 out of interest. And that's a famous anecdote. And they actually took the moth and they stuck it onto the notebook with a piece of sellotape. I think I also read that that's now in the Smithsonian or something. Anyway. So again, those of us that are familiar in verification and design, we know that good practice is to separate out into two disciplines as much as possible. And, you know, we develop verification engineers with a key set of competencies, and we develop design engineers with a complementary set of skills and experiences. But I guess the point I was trying to show on this slide, my Venn diagram, is, you know, there's a lot of overlap actually. So there's a lot of things that really fall in the middle. Verification engineers need to understand specifications. They need to be good at looking at RTL code as well, and looking at waveforms and running simulation. And they're also good at looking at data and, you know, scripting workflows. There's a whole raft of skills that really kind of fall in the middle. And then I think there's some that I picked out that I think are more unique either side. If you're wondering what ABC is, so this was something I heard on the radio a couple of weeks ago, where I think actually it was a police detective talking about ABC in terms of, you know, assume nothing, believe no one, and check everything. And I think when I heard that, I thought, yeah, actually, that's quite a good fit for verification as well, in terms of what we do. There's a certain mindset of verification engineers and, you know, how they go about doing their work. So, moving on to bugs then. So when is a bug a bug? So is it only a bug when you see it? So if you've got an unobservable bug that's somewhere in the design, is that still a bug? So I think these are interesting things to think about. So observable usually means that eventually you're going to see that bug manifest in some kind of error or failure. You can detect it, okay? You may not detect it straight away. It may be a long path before it actually emerges. And they can really fall into only 2 or 3 categories, I would say. So lockups is a category that is quite common. So it could be denial of service type problems. It might be deadlocks, live locks. You know, all of those things are easy to see happening in your verification environment. And actually, in actual fact, if that happens in the real world, you know, you might have some potential workaround, because you might be able to detect that and then reset and start again. So actually, those are probably the lesser evil in terms of bugs. The data corruption one, I think, is the worst one. So particularly if it's a silent data corruption. So if something gets corrupted in data and you don't detect that, then, you know, the consequences of that could be unknown. They could be large. So that's the one that you want to worry about. And then I remember from, you know, experience, we spent a lot of time talking about rare and how rare bugs are. And that's an interesting conversation when you think about how difficult it may be at verification time to expose a certain bug. You know, there could be, you might be running for days or weeks and, you know, billions of cycles before you hit a certain scenario. Because what appears to be rare in verification space is going to be, you know, annoyingly frequent when you're actually running on real silicon. So you have to bear in mind what you mean by rare. And then I was thinking about non-observable bugs. So what are those then? So how do you find those actually? So a lot of those I think are spotted by eyeballing code or eyeballing waveforms. They're accidentally discovered. Or, you know, if you're using formal techniques, then you might expose them through formal, because formal's good at showing all possible scenarios. So, you know, it may be that problem is being masked in your, you know, you may have multiple problems, that means that the first problem is hidden behind the second one and you don't see it. And I think whenever you're in that situation, you've got non-observable error. I think the team then have to take a decision about, well, how confident are we that we can clean this up and we fix it, or do we leave well alone? And those are kind of the engineering judgments that I think engineering teams are having to make. And then there's a whole bunch of other kind of categories or classes of bugs that I've called out here. So vulnerabilities, so things like Spectre, for example, was a classic vulnerability type of bug. So not something that normal operational code or sequence is ever going to trigger, but there is a path to trigger a sequence that maybe could cause a security breach or data leakage or whatever, with some convoluted code sequence. And those are really, can be really worrying bugs, particularly for products where security is a key issue, which actually is probably an awful lot of products these days. Then you've got, I'd say, a lower class of problems around things like you've got debug architectures, or aids to software development, such as event counters, whatever. Bugs in those things don't really break the parts, but they may make it more difficult to work with in terms of software development. I'm going to get a piece up here. So they got safety critical. So you're now talking about logic that's being added to your device to protect against single event upsets, maybe. You could have a bug in that logic. That bug may not be exposed until a single event upset event occurs. So how are you going to test for that? And these are going to be extremely rare events. But again, if you're talking about safety critical, then those are going to be critical bugs for a safety critical component. And then finally, performance and power. So maybe non-functional bugs, but bugs that where entitled performance may be lost. Again, how do you spot those? Maybe you've got some benchmarking performance suites of tests, or again, oftentimes I've seen designers in the past just eyeballing this stuff and going, hang on, that's not meant to work like that, and they've realised that there's a slow path where there could have been a faster path. And then finally, clocking and reset. So asynchronous events, domain crossing. There's a whole different area of verification. I think there's a talk on that later. That's who's talking about clock and reset verification. Mentor. Yeah, sorry. Okay. So here's one of my lovely hand-drawn diagrams. So this is a hypothesis, right? As I've said before, I'm not qualified. This is not real data. This is opinion and experience. And what I'm basically trying to say here is that if you look at the consumption of resources, which is the blue line, over the life of a development, and you see that escalating, usually escalating up to some kind of peak, and then maybe retaining a peak for a period of time, because you're essentially exploring the design, soaking it, and trying to wring out bugs. Many of the bugs are going to be found before you hit that peak, actually. So, these are going to be the easy bugs, essentially. They're going to be the low-lying fruit. You should be able to knock those out quickly with less effort. And really, it's this zone here where I think you're looking for the critical bugs, and they're smaller in numbers, but that can be a very long tail in experience. And so again, hypothesis, I'm saying probably 10% of the bugs are found with 70% of the resource consumption and effort. So if you're thinking about where to improve your flows, that's the area where potentially you've got the best ROI. And then also thinking about root causes. So essentially bugs are injected into the code, into the RTL code, either when you're authoring the code in the first place, and some amount will go in there. I don't have good analysis on that. And a lot of them are probably going in as the code changes. So as the code is churning and you're committing changes all the time, you're either committing those changes to fix bugs or performance tuning, or maybe for identifying missing code. And I think it's a lot of those changes is where a lot of bugs get introduced into the design. Some of them are, root causes go back to specifications, whether it's the specs or the interface specs. If you get those wrong, they're going to propagate into your design potentially. Some of them are just simple typos and copy-paste errors, as anybody, whether you're a software developer or a hardware developer, knows that copy-paste and typos is the curse of code authoring. Maybe if you've got a good IDE, you can try and minimise that to some extent, but I don't think we really know how to get away from that kind of human error type problem. So I'm just going to have a quick word on complexity. So, so we often talk about complexity actually, particularly if we're developing complex products or complex hardware IPs. There's a lot of challenges related to complexity, and I think there's complexity for a good reason, and there's complexity for bad reasons. So it's complicated because the architecture is complicated, or the goals and the targets of the product are complicated, and you have to do a lot of clever tricks. There's a whole catalogue of clever design tricks that people are using to build optimal, high-performing solutions. So that's required. Other complexity, I think, is introduced. So particularly when the behaviour is no longer understood. So if the designers themselves are starting to lose a grip on understanding that behaviour, then you're almost certainly in a situation where the code quality is degrading and you're likely to end up with bugs. I was thinking about complexity and whether that would be measurable. How great would it be if you could track and plot complexity over time? If you could reason about different complexity numbers. There are some works on this. I won't go through the details now because I'm going to run out of time, but cyclomatic complexity is one that's worth looking at. Again, mostly comes from the software side of the world, but there have been some cases where people try to apply it to hardware as well. So what are the strategies around trying to avoid some of these bugs? So I'm not going to go through this because I think this is all well documented and historical fact that most people are already familiar with this kind of thing. So assertions we've talked about before, other DVClub events, I think, formal verification, I think we're coming on to with one spin later as well. And there's a feature toggle bits, I think they're called something else at my last company, but the ability for designers to be able to turn off some features in the design and basically roll out or back out kind of risky capability, shall I say. But I wanted to make a book recommendation. So one of the things that I was doing about a year ago was running a software development team. And I started reading about more agile flows and DevOps. And actually reading that book, so this is a good book I recommend if you want an introduction to it. There are plenty of others out there, but I like this one. Gets you to think about, okay, so software developers actually also have really challenging issues, particularly when they're developing platforms that, we're all using those platforms. Many of them are, critical platforms in the field. I heard on the radio this morning they were talking about Uber. And obviously their whole business is based on a software platform. Those platforms have to be super reliable. They can't afford to, do a bad update and then wait for 2 weeks while the design team issue a patch. So there's a whole bunch, I think, of potential things that come out of DevOps that are worth looking at. Some of them I think are already becoming established in hardware. So particularly around continuous integration tools. So you've got Jenkins or you've got commercial offerings there. I think there's a trend towards, I call this pair programming, but people are using Gerrit. Again, software communities are using this as quite commonly now, but giving you that ability to do pair code reviewing is very powerful. And then other things like, swarming on defects. So when a bug comes up, you actually swarm on that and solve that problem quickly. And then code refactoring, I think, is another important thing, that building that refactoring time into the plan, which is what DevOps talks about, to make sure that you do have that opportunity to go back and clean up the code, which is improving the code health. So how much longer? 2. Right, I'm going to have to jump to the end. Okay, so I'm going to skip over coverage analytics because it's kind of obvious and we've talked about it in DVClub many times before. Bug analytics, so, you know, what does the bug curve look like? Anybody that's in verification familiar with that. So correlating data. So if you look at the bug data and then correlate that with actual, you know, execution data or check-in data, and I think I talked about this at Verification Futures event a couple of years ago, that is also very powerful. And then bug prediction was, I was just linking back to, I found this one from a guy called Greg Smith Oracle in 2011. I remember him presenting at DVClub about bug prediction model. And I think since then, I think the world's moved on. Again, if you search for this stuff, you will find that there's quite a few papers about how to do this in software, and they're mostly based around data science, machine learning techniques these days. So, getting towards the end now. So a final thing I want to throw out, another book recommendation. So again, another idea that I think is coming from the software world, something that I looked at a couple of years ago with this, and I thought it was interesting, and I haven't seen a strong adoption of it in hardware world yet. But the Git repository is actually a fantastically rich source of data around how your development is progressing. And what this guy's done is he's come up with some visualization around that. So you can look at hierarchically what your design looks like in terms of modules. And then he talks about hotspots. So hotspot being a component that's complex, which I think is defined by the size. And then the color defines, you know, how many check-ins or commits have happened on that block. So, you know, it's not always related to the size. You've got a small dark one there. So that gives you some insights into what's going on in your code base. You've also got all the information about who the users are, who the people committed all those changes, and you can build up a picture from a user point of view to see, you know, who's owning all the code. Is there any code that's actually abandoned? Effectively, somebody's left maybe, and nobody owns that code anymore. What are you going to do? You're going to rewrite it, or you're going to, you know, try and adopt it. I think that is my apologies if anyone's still eating their lunch.
Okay, thank you very much, Bryan. Thank you.